Hello students, I am Dr. Tanmay Vishwas. I welcome you all in my channel Chemistry the Mystery of Molecules. So I hope you all are fine and you are following the rules and regulation imposed by your local authorities. You should cooperate with them in order to keep the situation under control. Okay? So like other days, today I am going to discuss another interesting topic of chemistry, that is decarboxylation of beta-keto acid. The basic concept and mechanism. This thing we will cover today. Actually, the main thing that beta-keto acid or beta double bond, multiple bond acids decarboxylate very easily compared to traditional carboxylic acid. This is the main thing of our today's discussion, and today's talk will cover few points like the basic idea, reaction mechanism, transition state, and driving force for this process, and at end we will discuss about the intermediate and how this could be tracked. So a lot of chemistry to be learned in this lecture. So let's go forward. Okay. So this is actually named as beta-keto acid. Why? See, this is the carboxylic acid. This is the alpha carbon. This is the beta. In beta position, keto is there. That's why this is called beta-keto acid. Not only keto, there should be double bond, alkene or nitrile. Those things means beta multiple bond acid. Better to say beta multiple bond acid. They undergo decarboxylation very easily. Means if you compare this with traditional reagent, like for example, let's take this, and you want to decarboxylate it. So compared to this decarboxylation is facile. Okay, so this decarboxylation is facile. Question why? That is the thing for our today's discussion. This is when we say something is facile, that means the intermediate is stabilized. Simple logic. Intermediate is relatively stable, better to say. Relatively stable. So when I say intermediate is relatively stable, then one conclusion comes is that intermediate is relatively stable means it is generally, in case of generally, the electron is delocalized, because delocalization means stabilization. So that is the overall thing is responsible for this. Okay, so let's discuss slowly. Now let's go to the mechanism part. How this reaction happens. So what happens if you heat this? It undergo a cyclic transition state. Okay, how that looks like? Transition state means the bond which formed or broken, we will consider those. And we will keep the bonds which are not involved in this process. This dotted line means that these bonds are not, this simple line means these bonds are not involved in the transition state. Okay, so this is very difficult, or sometimes it becomes difficult because we do mistakes. See, this dotted line indicates that bond is formed or broken. Okay, so what this is a transition state. So this is the TS. Okay, now what happens in next step? Next step, this converted into a enol derivative, better to say, plus carbon dioxide, and that enol tautomerizes into the corresponding keto. By the way, there is another strategy to represent this story. How we can represent this in this way? Means in every case it is not possible to show that transition state. For that purpose we can present it in this way, means lone pair, or better to say that this will give, this will come, it will go, it will come back, and this. So you can omit this thing also. Fine. So in this way this bond is broken. But so overall this is some important things are very keep in mind. Okay. So first of all, what is the driving force? One is carbon dioxide is eliminated, which is a very stable molecule. Number 1 point. Number 2, it's a gas. Means it goes easily outside the reaction medium, so the equilibrium reaction can proceed further. First point. Second point, see, it's my opinion. How many number of bonds are broken? Check. This bond contains 2 electrons. This is broken. This is broken, contain 2 electrons. And this is broken, contain 2 electrons. I repeat again for your understanding. See, this bond is broken because see, this is a single bond, so 2 electrons. This bond is broken because it is completely gone, 2 electrons, and OH is gone from there, so 2 electrons. You can consider there is a OH making, no, that's a fine. We have considered all previously this, so this is 2 bond. So actually, so 6 electrons involved in the TS. What does it mean? See, during the transition state, it's a planar. So TS is planar. And if you see the product, this is actually a enol. What do I mean? That this carbon contains a p orbital. P orbital, and it is sp2 hybridized. Although it is previously, this is sp3, fine, I agree. But after the reaction, it forms the sp2 hybridization. It means that p orbital is generated. So you can consider one p orbital during there. P orbital was previously here. This is a carbonyl group p orbital there. Oxygen was there, sp2, and hydrogen no p orbital. It's s orbital, but it is vacant. So we may consider, it's my personal opinion, aromatic type TS. Why I am taking aromatic? Why I am saying this word type? Because all the criteria is not fulfilled, but some are like fulfilled. And why I am telling this word aromatic? Because aromaticity means stability, and here the TS is stable. But do I mean that it is stable like benzene? No, never. Because benzene is extremely stable. But this TS is somewhat little more stable. In order to make you understand this statement, I am telling this. Okay? So, just I am telling, it's my personal opinion. Think about, read, and if you think I am wrong, please mention in the comment box. So, this is in this way, this enol is produced, and carbon dioxide, this enol, after this tautomerization produces the carbon. So what we are actually getting? So we may consider that this is a method to prepare carbonyl compound. Method to prepare C double bond O. Or if it is alkene, then alkene. Fine. So this is the thing. So we have discussed about the transition state driving force. Now let's discuss about the intermediate. Okay, let me clean a little bit. So you can see what is the intermediate actually. Actually we can say the enol is our intermediate. Okay, because this is it is produced after the transition state and then it converted to the ketone. So enol is our intermediate. So is it possible to trap the intermediate? Yes. During the process, if you used bromine in the reaction medium, then we can get alpha bromo product. Okay. So what we can get? Bromine, if you used, then this enol will react this. Okay, and generally what are the condition is like bromine in sodium acetate acetic acid. It's a buffer. Sorry. This is, and what it resulted, this reaction resulted a alpha bromo compound. Okay, so this is the proof of the mechanism and intermediate trapping. So this is intermediate trapping. Now question, what is the profit? See, generally previously we have read that if you take a carbonyl under acidic condition, if you take for example bromine in acetic acid, if you do, then monohalogenation possible and it happens on the more substituted. So this is we can prepare. We have already studied. So this reaction, but if you have a sensitive functional group, under this condition, if it not stable, then this could be a bypass route. I know there is a very less difference, point number one. Second, if you don't have a free, here one thing is essential is enolization. Here the most important point is this enolization. Enolization is directly not possible. There is a carboxylic acid, so you can decarboxylate and produce the enol as an intermediate. So that is the uniqueness of this process. Okay, so this is the way to trap the intermediate. Now some other let's discuss some other type of this beta-keto derivative. Okay, what do I mean? You have already read that ethyl acetoacetate means, better to say acetoacetic acid. This malonic acid, this malonic acid ester dimethyl malonate is a very famous compound, and see these all are active methylene compounds. This, okay, if there is substitution, that's a different, but if this is hydrogen, this is very useful because it's an active methylene compound. Ethyl cyanoacetic acid. Similar, see this is not C double bond O, this is C double bond N multiple. That shows. Even you may consider that C double bond C. Such type of derivative also. Because mechanism is similar. Not, sorry, I made mistake. So, see mechanism is similar. This is a alpha, this is beta. So all shows this property. Even, but one information that see if I tell that this beta-keto acid undergo facile decarboxylation, fine. Then a question comes: can we prepare this compound? If it is prone to facile decarboxylation, is it really possible to prepare this compound? Actually speaking, yes, it is possible to prepare this compound. It is possible to prepare this compound. How? First, you have to prepare this compound, but temperature, no heat. You can't give any heat. Then stable, because see one important information: beta-keto acid doesn't mean it will undergo decarboxylation. You have to give heat. So if you don't provide heat, it will, this material will remain in the stable form. Okay, so this important information also, because sometimes we believe if we learn it but we learn it incompletely, then there is a problem. So now let's discuss one example, very interesting example. The example is, see this material, this thing, acetoacetic acid undergo facile decarboxylation upon heating, means it means you cannot decarbox. So it means it can't be distilled, which means it will decompose. Means decarboxylation will happen. Fine. But one interesting example is that if you take this derivative, CF3, then distillation is possible. Distillation is possible. Previously, distillation was impossible because it decomposes, but this is possible. Fine. First of all, if you look at the transition state, just I have shown this, because of the minus I effect of this, point number 1. So point number 1. So point number 1 is minus I effect of CF3 hinders the protonation. What do I mean? Means we can write little different way. This means we can think that it will give, this will come, it will. In this way decarboxylation is expected to happen, and what it will result? This is CF3 COH double bond CH2. Fine. So this protonation is hindered because the minus withdrawing effect of CF3. Point number 1. And point number 2. Hydrogen bonding. Hydrogen bonding does not allow the 6-member TS. I will explain. Keep this thing in mind because such type of question could be asked in your viva. That beta-keto acid undergo decarboxylation very easily, but why these don't undergo decarboxylation efficiently? Okay, so how? Let's draw the molecule. Actually, it is our opinion that it should undergo decarboxylation in this way, but it doesn't. So this is a wrong. What actually happens? So you may think in this way. This is the C double bond O. This is the CF. Here F2. Okay. So there is a hydrogen bonding. What do I mean? This fluorine hydrogen, and it's a very strong hydrogen bonding. Very strong hydrogen bonding, because we know the form fluorine oxygen hydrogen form very strong hydrogen bonding, and fluorine has a very good reputation of forming very strong hydrogen bonding. Example of this, that fluorine is a mono HF. HF is a mono acid, means it should give salt of simple MF we can expect, but only HF is example where you can get this salt ammonium HF2 minus. This is plus minus. Why? Because this fluorine hydrogen bonding, this is a very stable, and actually this is a equivalent. This is a very strong bond, and you can't distinguish which one is the HF bond and which one is the hydrogen fluorine hydrogen bond. Okay, this is very strong bond. So that is the interesting thing for this fluorine form. And now you may think, sir, is it looking little odd? No, it is not odd. Why? See, let's guess the number 1, 2, 3, 4, 5, 6, 7. So it's a 7-member hydrogen bonding. 7-member ring is formed. Ring formed because of hydrogen bonding. So what is the advantage of this? That if 7-member ring is formed because of hydrogen bonding, 7-member ring is stable. It's not very unstable. So it can form, and this is the reason that it doesn't undergo decarboxylation very easily. Whether its corresponding CH3 analog undergo decarboxylation easily. Okay, so this is the overall discussion for today about decarboxylation of beta-keto acid. So what you have learned? We have learned about the mechanism, transition state, factors stabilizing the transition state, even why this reaction happens very easily, and most importantly how to trap the intermediate proof of concept. And most importantly, at the end, we have discussed one very important question, that is why this CF3 derivative doesn't undergo decarboxylation very easily, whereas the CH3 undergo. Okay, so a lot of chemistry we have learned in this topic. So I hope this video is useful. Thank you for watching this video. If you really enjoy my teaching, Please help my channel to grow. First of all, subscribe my channel Chemistry the Mystery of Molecule, and please press the bell icon to get the notification of every single video I upload. Secondly, share this video among your friends such that many people could be benefited from my effort. And most importantly, please like the video and make some good comments because it inspires a lot. And if you think some rectification is essential, please feel free to mention in the comment box. I will try to improvise my teaching accordingly. Thank you again. Stay happy, stay blessed. See you in my next video.